Good morning, everybody. So first of all, let me thank the organizers for allowing me to present this talk here. So today I'm going to talk about a phenomenon of the inertial frame dragging, which is a fundamental effect that occurs in general relativity. And I'm going to present to you a toy model for its quantum detection. So just to warn you, so contrary to the previous talks, this really is a toy theoretical fantasy rather than the actual proposal for an experiment. So what is a frame dragging, or sometimes called gravitomagnetism? So it is a general relativistic effect due to the motion and in particular rotation of matter, but also of gravitational waves. And in many respects, this is actually very analogous to electromagnetic induction. So I just remind you that already in the weak field approximation of the general relativity, when we actually include the currents for the matter, then there is a corresponding GTI cross term in the metric, which we can call AI. And then surprisingly, the Einstein equations just give you the standard Maxwell equations in the Lorentz gauge, provided that we impose the harmonic gauge for perturbation. And the geodesic equation gives you basically, well, in the first in the zeroth order, it just gives you the electric force, but in the next order in velocity of the sources, it also gives you the Lorentz force over here. So of course, this realization goes back to the early days of general relativity. So already Lenzi and Turing in 1918, they wrote down a metric for a slowly rotating object.
Sorry, are you moving the slides?
Yes, I am.
Oh, sorry, we cannot see it. It's stopped and it's not even in complete.
I see. So what do I do now? Should I try stop sharing and start sharing again? Let me try that.
I think you have to go. It says Sebastian says that you have to do the presentation mode first and then share the window.
Okay, let me try that.
Okay, now I think.
Just a second. So. I see.
I think it worked now, but.
Okay.
Don't worry.
So now let me try again.
Yeah, now we are in the frame dragging gravitomagnetism slide.
Yes, and can you see me changing the slides?
Yeah. Now it's perfect.
Really?
At least it has changed. Can you change another one just in case? Okay, now it stopped.
Okay. Okay, let me try something else. I'm sorry for this.
Yeah, no worry. So if you want, you can send it to me, or okay, let's try again.
Okay. So what about now? Can you see changing slides?
Yeah. Now it's fine, I think.
Can you see it? Can you hear me as well?
Yeah, we can hear you, and you are in the quantum detection of inertial frame dragging slide. Can you change just to see? Okay.
Can you hear me as well?
Yeah, we can hear you.
Okay, I'm sorry for that. So let me start from the second slide. I already took 6 minutes. Okay, so let me start again from the frame dragging. So it's a general relativistic effect due to the motion and particular rotation of matter and gravitational waves that is analogous to electromagnetic induction. And so, what you have to do is that already in the weak field approximation, T mu nu not only has the energy density over here, but also has the mass currents. And so once you include these mass currents, then you also get this cross term GTI cross term, which is parameterized by this AI. And surprisingly, the Einstein equations just reduce to the Maxwell equations as we know them. But also the geodesic equation reduces to basically the Lorentz force law. All right. So now this was already realized by Lense and Turing in 1918. And so basically what they did is that they constructed the metric for a slowly rotating body. And similarly to electromagnetism, if you have charged sphere and you rotate it, the sphere creates a magnetic field. So now this one, of course, creates the gravitomagnetic field. And due to the Lorentz force, if you send the radio geodesics in, then of course this Lorentz force will push your geodesics to start rotating with the rotating body. And so here's the corresponding Coriolis type force, but you can also say, well, you can interpret this as the space-time outside of the rotating body is actually dragged along the body, along the rotation itself. So similarly, if you place a gyroscope, in this, around this gravitomagnetic field, the gyroscope will precess around these magnetic field lines. And this is nothing else than what we know from electromagnetism as Larmor precession, if you have magnetic moment precessing around the magnetic field. So of course, everybody is more familiar with the extremal example of frame dragging, which happens around the full solution of general relativity around Kerr black hole. And we know there is an ergosphere, and in that ergosphere, everything has to corrotate with the black hole, so that the space-time is completely tracked. And this has very many astrophysical applications. For example, the Bardeen-Peterson effect, which implies that your accretion disk around the black hole will eventually actually align with the black hole spin. So has this been measured? It has, classically. And so there's this famous gravity probe B experiment. So basically people launched a satellite which on the orbit around above the North Pole. And then you observe two effects. One of them, which is called here the geodesic effect, is if the Earth was not rotating and you just had the parallel transport of your gyroscope spin. However, because the Earth is rotating, you also get the frame dragging effect in the direction of rotation. So now if you see all these things agree with the experiment, but you also notice what is important for us is that the geodesic precession is actually about 300 times or 200 times bigger than the frame dragging effect around the Earth. So now what I want to do is I want to give you a very toy model for this quantum detection. And so what we proposed in the paper, which I cite in a minute, is that let's consider a rotating shell. And so you can arrange that this rotating shell inside has completely flat Minkowski spacetime. But because of the rotation of the shell, the interior will actually rotate with respect to distant stars. So now what we do next is that we place the Unruh De-Witt detector inside, and we are asking, can this detector actually notice that it's rotating with respect to these distant stars? And summary is yes. And actually, this can happen in the time scales, which are much faster than that would be possible classically. So classically, you would have to send a signal from the detector to the shell. The signal would have to bounce back, and then you would know that the detector is inside the shell, and then the shell is actually rotating. So quantum mechanically, even from vacuum, you can detect that almost immediately. And so my talk is based on these three papers, and the most fundamental one is the first one, where I was not an author, but really the quantum detection of inertial frame dragging is over here. All right, so let me give you a little bit more details about this summary. So you have to consider what is the metric inside, what is the metric outside. So outside, we take care to the linear order in A. So this is basically like a Lense-Turing spacetime, but we just completed square here. Inside, you can arrange that the inside is completely flat. So if you look at this metric over here, so capital R is the radius of the sphere, so it's a constant. So now if you introduce new variable, this phi over here, then you see that this space-time is really flat space-time, right? But what it also means is that, of course, from the asymptotic observer close to distant stars, this phi is important. And so if you place, the observer on constant this phi here, then the the inside of the shell is actually rotating with respect to that phi according to this formula over here. So the inside is actually tracked with respect to distant stars. So now these two metrics can be matched by using the Israel junction conditions, and you can achieve that by using the shell to be identified with the perfect fluid. So here is again the picture summary. So you have the rotation out of this, well, it's basically care, and the rotation is dying out as you go to distant stars. Inside is rotating at a constant angular velocity, and the shell is composed of that perfect fluid. And so if you put an observer or a detector inside the shell, it sees just the flat space. So there are no Christoffel symbols, no nothing. So it's just inertial observer. And so if it correlates with the inside, it rotates with respect to the distant stars. All right, so now how do we do this detection? So we consider a scalar field in vacuum. So here's your decomposition into the modes. We can use spherical harmonics to the linear order in A of the rotation. Then inside you can easily solve because it's just flat space. So you have a solution in terms of those Bessel functions. Outside, you have to numerically integrate, but you also have to provide some, initial conditions of boundary data for your integration. And so you basically have to extend the psi through the shell, and you do it in such a way that psi is continuous, but the derivatives are not necessarily continuous. You have to also normalize the solution properly. So now UDW detector, this is the standard model as we use it. So we use the detector gap to be capital omega. But what may be a little bit different is that we really want to make sure how long the detection takes occurs, and so we actually use the compact support switching function. So really the detector is only switched in for a finite period of time. So instead of Gaussian switching as people typically use, we use this switching function over here. All right, so now this is again the standard stuff. So if we start with the detector in the vacuum state, then what is the probability to excite this detector? It's given over here by this formula. So all you need to know is to calculate the Weidmann function, which is over here, and it's given by your mode expansion over there. So now we place the detector inside the shell. So we put it on some distance from the origin and distance from the shell, and then we place it on theta equal to pi half, and it's an inertia detector inside the shell. Of course, that means that the detector actually rotates with respect to distant stars by this phi over here. And so here are the results. So first, so this is the response function over here. You have to calculate this numerically. And so let me first switch off the rotation. So A is 0. And then you can compare, whether the detector can actually, detect that there is a shell. And so this really shows the response function of the Minkowski space with respect to just the shell without rotation. And you see that this is sort of symmetric, with respect to the detector gap. So positive omega is you want to excite the detector. Negative omega is you start in with the excited state and you want to de-excite the detector. But once you add the rotation, you get a difference between the static and rotating case. The difference, if you look at the static versus Minkowski, is basically 10 to minus 5. But rotating versus static is 10 to minus 7. So again, it's something like 100 times smaller, the rotational effect over here. All right, so that's what we have done. Of course, this calculation has many problems. Some of them are even theoretical, not only experimental. So one of them is that we really took the metric to be to the linear order in rotation parameter, and this should be good as far as this quantity here is small. However, the detection is really at the level of OA square. So, it can be, qualitatively it's probably correct, but quantitatively it may not be. So, what are the alternatives? How to improve this model? Well, first, you don't do anything. You just say, well, this is just a kinematic effect. We don't really need a vacuum space time. And so, there will be some TMU supporting our space time, and that's fine. And then, these are the effects, kinematic effects. The other one is to use, exact shells to higher orders in A. And there are such exact shells, but this will be numerically, very difficult to do because you no longer can separate your scalar field into modes and stuff like that. Finally, the most promising maybe is to use, instead of shells, is to use cylinders. And so the advantage is that you get trivial separable solutions for the scalar field, but the price to pay is that you have a bad fall off of fields at infinity. And so there was a proposal by Davies that actually this fall off at infinity can be sort of solved by placing two cylinders where you introduce another outer cylinder which is counter-rotating, and that solves some problems of this fall off at infinity. And we use that to actually say something that outside of the cylinder there's a conical deficit, and the detector inside the cylinder actually can detect that. But anyway, so this is a work in progress whether you can use these cylinders to say to predict the inertial frame dragging to any order in A. So summary. So inertial frame dragging is one of the fundamental predictions of GR that has only recently been observed by classical observations. So I was trying to propose here a toy example of slowly rotating shell where you can actually, in principle, detect this quantum mechanically. And so, this can be upgraded by considering either, the cylinders or considering, some analog spacetimes, or maybe the best way is to actually use cylinders instead of the shell. So thank you so much.
Thank you, David, for this nice talk. I think we are a bit out of time, so I will suggest that the discussion or questions about this talk could be arranged in Slack if there's no problem with that. So we can have a half short break. So thank you again, David.